Hi everyone, this is Dr. Swaminathan S.M., Associate Professor, EC Department, SNS College of Technology. Now I am going to discuss about the topic called Impulse and Step Response Analysis of Second Order System. So last class we will discuss about the previous class we discussed about the first order impulse response and step response. So today we are going to discuss about the impulse and step response of second order system. So first the introduction and second order system, and next step response of the second order system. Following with the activity, we'll discuss about the impulse response of the second order system, then damping ratio for undamped, that is equal to 0, for underdamped means 0 to 1, critically damped means equal to 1, over damped means greater than 1. Next summary. So the second order system, the effect on the location of the poles and zeros, transient response of the first order system, we already discussed. Compared to the first order system, second order system is used widely responses, so it must be analyzed and described. Next, varying the first order system parameter t comma k for simply changes the speed of the offset of the response. Next, the changes of the parameters for the second order system, that means second order system can display the characteristics of the first order system or based on the transient response analysis. So we'll discuss about the introduction. Omega n square divided by s into s plus 2 sigma omega n, that is a negative feedback, it is connected. So c of s divided by r of s equal to g of s divided by 1 plus g of s. So this is the transfer function. Next, based on this transfer function, omega n, that is natural frequency of undamped for the second order system, is the frequency of the oscillation without the damping, and the damping ratio tau, that is second order system, which is a measure of the degree resistance to change in the this system output. Next, they determine the undamped natural frequency for undamped ratio c of s divided by r of s. So for the given value, so you can get omega n squared divided by s squared plus 2 sigma omega ns plus omega n squared. You just compare the denominator and the numerator, then you can get omega n squared is equal to 4 and s squared plus 2s plus 4, that is compared with the denominator of the system. So omega n is equal to 2, so just to substitute the value, then you can get the 2 sigma omega n is equal to 2s. Next to sigma omega n is equal to 1, because omega n is equal to 2, then you can get the tau value 0.5. So based on this given system, the two poles, one is minus omega n tau plus omega n root of tau squared minus 1, that is the same thing, minus in between the tau and omega. So these are all the two poles of the system. So according to the value of the tau, you can get the four categories: over damped, under damped, that is over damped means tau greater than 1, and under damped, that means 0 to 1, that is the value 0 to 1. And according to the set of the value in the two categories, another two categories, undamped, that is tau is equal to 0, there is no values, that is two poles are having imaginary poles. And next, according to the value of tau, a second order system can be set into the one of the four categories. So critically damped means tau is equal to 1. So the second order system, it consists c of s divided by r of s, the particular value. Then you can get the characteristic equations like s value. So just to substitute the value, the two roots are imaginary axis, tau is equal to 0, and two roots are real and equal, tau is equal to 1. Two roots are real but not equal, tau greater than 1. Two roots are complex conjugate, then tau is the value 0 to 1. C of s is equal to, that's the value. So C of s is the Laplace transform of the C of t. R of s same for R of t, and omega n is the natural frequency, and tau is the damping ratio. So the step response of the another system, R of s equal to 1 by s, then you can get the value of the system. The case 1, tau is equal to 0, so just to substitute the value tau is equal to 0, then you can get the equation R of s equal to 1 by s from the given equation. So you can get the inverse Laplace transform to get C of t from C of s. So you can get this value. And the same thing, case 2, for tau is equal to 1, so you can get the transfer function, and based on this you can get the inverse Laplace transform to get C of t from C of s. And next, the following with the activity, the impulse response of the second order system, it defines by using these two different methods. Following the procedures by considering the value r of s, that is equal to 1, and next to the differentiation, then you can get the value. So for the condition of damping ratio tau is equal to 0, so you can get the omega n sin omega n t, and omega, that is tau is equal to 1, just substitute, and tau is equal to value 0 to 1, and tau is equal to greater than 1, you can get the impulse response based on the damping ratio. So the damping ratio, it is defined the 2 plus 2, that is 2 is called underdamped, and third, fourth one is called critically and overdamped. For the characteristic equation, you can get the damping ratio tau is equal to minus tau omega n plus or minus omega n root of tau squared minus 1. So the roots are given the value tau is equal to 0 and tau is equal to 1, tau is equal to, that is greater than 1, tau between 0 to 1. So tau is equal to 0 means imaginary, equal to 1 means real and equal, greater than 1 means real and unequal, and 0 to 1 means it is called complex conjugate. So the undamped system, that is C of s divided by R of s equal to omega n squared divided by s squared plus 2 sigma omega ns plus omega n squared. So value underdamped means you can get tau is equal to 0, then you can get the C of t and get the transfer function of the system. And tau is equal to 1, that is the same thing for critically undamped. So you can get the value. So this is called the step response of the second order system. Thank you.